It's great to have. Great. So it's great to have Professor Ken Burch here to give our CM seminar, and he's going to be telling us about the tools that he uses in his lab to study a range of quantum materials, including the very kind of newfangled YL semimetals. Professor Burch is an expert in all things optics, and has looked at all sorts of things, including magnetism, all the way to the very recent topological materials. And so with that, we're very privileged to have him here to tell us a bit about what he's been doing. Right. So thanks very much, Ken.
Thanks, Justin, for the very nice introduction, and thank you everyone for being here. So I know it's early there, but it's late here. So on the off chance I fall asleep in my own talk, I'll just give a kind of a brief 5-minute overview of what I'm going to tell you today. So I'll start by talking about sort of what is it that I think is sort of the main, or maybe a main challenge in quantum materials. And, at the end of the day, why are we interested in these materials? It's because they have, a variety of these sort of fundamental electronic or quantum, if you will, properties that couple to a whole host of their responses. And most importantly, I think, or I shouldn't say most importantly, but one of the most interesting sort of cases is where, various pieces of the puzzle, if you will, interact, right? So the spin coupling with the lattice and with the orbital components, leading to new kinds of behavior. And one of the challenges, how do we identify these new phases of matter as they emerge? And how do we understand the sort of relevant roles of the different pieces in these quantum materials? So with that in mind, I will introduce you to Raman scattering, which, as I will tell you in a minute, was actually developed right after the Spanish flu, so perhaps relevant to modern times in that sense. But basically, the idea is you send light in, and I will give you a kind of different way of thinking about this, but your photon will scatter, and as a result, make an excitation, and that excitation can be a lattice excitation, like a phonon. It can also be a magnon or a spinon. It can be a plasmon, and so as a result, when it scatters, you can, of course, measure the energy of these wide variety of different physical excitations, but you can gain a whole lot of other information about their properties. So by looking at the polarization dependence, you can learn about the symmetry. By measuring the temperature dependence, you can learn about the statistics of the mode. So there's really a kind of host of information that's available to us in this tool. So I'll give you some very brief examples at that point, but then I will sort of dive into two kind of most recent examples that my lab has worked on. The first is trying to tackle this problem of understanding transport in topological semimetals. So one of the kind of mysteries in this field for a few years has been there's a wide variety of these topological semimetals that have these enormous transport mobilities, but at the same time, orders of magnitude lower single particle mobilities. And so we wanted to really understand what's the origin of that, because it's not so clear that there's quantum geometry or topology has anything to do with it, because you basically see this effect in everything from Dirac semimetals to WP2, which is technically a type 2 Weil semimetal, but the node is far, far buried below the Fermi surface. So we had a hunch that the phonons had something to do with this. And as I will show you, we now have direct evidence from Raman that the phonons strongly couple back into the electrons. And so what that means is normally when you try to do transport, of course, electrons can scatter into phonons, phonons scatter into other phonons, and you lose the energy and momentum. And that's basically, where it goes into heat. But if you have the case like we have here, where the phonon electron scattering is strong, that momentum is actually mostly recovered by the electron bath. And as a result, you have this kind of strongly coupled electron phonon fluid, which can then carry the energy and momenta and give you these very long apparent transport lifetimes, even though your single particle scattering rate is, of course, much, much lower. So I'll then switch into the work we've been doing on 2D materials. And in particular, I'll tell you about one that we're quite excited about, ruthenium chloride. I actually won't talk at all about, for the most part, about its magnetic responses, which are by themselves quite interesting. And here I'll focus on its electronic structure. What's unique about ruthenium chloride is you have a very deep work function of about 6.1 electron volts, but that's coupled with a very small band gap of about 1 eV and a very narrow conduction band. And so what that means is that this ruthenium chloride essentially acts like an acceptor in the sense of an old sort of old school semiconductor language, which is to say that if you put graphene on it, it will just soak charge out of graphene. So you can actually get to a Fermi level of about 600 MeV in the graphene just by placing it directly on ruthenium chloride. What's more, because this charge is so enormous and comes from this charge transfer, it's also very short in length scale, as I will show you. And what's more remarkable is the valence band of HBN basically lines up with the conduction band of ruthenium chloride, so that you can still get a charge transfer even with HBN in the middle. So I will show you the various things we've done to kind of optimize this effect and also to measure it using Raman scattering. And here I'm showing, roughly speaking, the extracted charge when we have ruthenium chloride sitting either directly on monolayer graphene or sitting with a BN layer between the monolayer graphene and the ruthenium chloride. And what you see is that in the monolayer graphene directly touching the ruthenium chloride, you get a very large charge transfer on the order of 310 to the 13, more than you can get with a backgate. And when the BN is in the middle, you actually still get some charge transfer, although in this case lower because the BN was fairly thick. And what's even more remarkable is that the length scales over which this occurs are extremely short, so that you can always basically, by our resolution, see this charge transfer seems to be fairly immediate, both in the lateral and vertical directions. Last but not least, if I have time, I will tell you about a variety of different new directions we're going in. One is using Raman to measure quantum interference, but the other is actually taking quantum materials and making them useful in the post-pandemic world. So in my group, we've developed what we call a clean room in a glove box, where we can do all of the fabrication and not just 2D transfer, but for example, the lithography, Raman, and AFM characterization, all in this inert atmosphere. And so that allows us to rapidly make new devices of various kinds, one of which we're focused on is developing CVD graphene as a multiplex biosensor, so that we can actually detect various kinds of different respiratory infections very rapidly and accurately. Unfortunately, I have no time to talk about that today, so if you're interested, send me an email and I'll gladly tell you more. So as I mentioned, we're quite interested in these quantum materials. And as we're all quite aware these days, our interconnected world has made it really crucial to develop detectors of emergent particles. That is, of course, also true in quantum materials, where we want to find the excitations that emerge as these kind of couplings happen between different order parameters, and as we enter into new phases of matter. But of course, we'd like to also have a tool that can tell us about the different kind of fundamental aspects of these quantum materials. So for example, using them to look at scattering, say between electrons and phonons or vice versa, to see how we can understand sort of their transport properties, or say coupling between different parameters. Of course, it would be nice to also look at their symmetries, you know, whether we're thinking about Landau phases and broken symmetries, or how different symmetries are protecting states to different response functions. Or of course, their quantum properties, whether it's the relative phases between different pathways, their quantum geometries, or even the statistics that can emerge from new quantum phases of matter. So one optical tool that we've been very excited about in my group, which I am unfortunately not going to talk about today, is using nonlinear responses as a way of probing some of this. But if you want to learn more about that, we recently published a review article in Nature Materials with my colleague Chung Ma and collaborator Adolfo Grushin, which sort of talks about the various ways in which nonlinear responses can be useful in measuring and looking at and even controlling quantum materials. Okay, but I'm not going to talk about that today. I'm going to talk about a slightly older tool. So it turns out, as you may know, that the last pandemic was the 1918 Spanish flu, which lasted till about 1920. And in 1922, Raman traveled from India and he was on the Mediterranean on a ship, and he was thinking about Rayleigh scattering as explaining, the beautiful blue sky. And he looked at the Mediterranean and wondered whether light scattering could also explain why the Mediterranean is so beautifully blue. Is there some interconnected part of that? He was so excited about that idea that as soon as he gets back to India, he goes and starts measuring light scattering, actually using a telescope with a sun. It's kind of amazing. Anyway, he measures light scattering from various fluids and discovers what we now call Raman scattering. And so indeed, this is a tool invented right after the last pandemic when people could travel again. And I think we're all looking forward to such days as well. But in any event, so I want to tell you about a way of thinking about Raman scattering and why it's so powerful, which is also slightly different than our more modern way of discussing it, but I think is the most useful. So whenever you have an optical response, you're thinking about applying an AC field, and you have some polarizability inducing some AC dipole in your material. Of course, that polarizability can always couple to some to some operator. And so I can always expand that polarizability in terms of the first derivative in terms of that operator times the fluctuations of that operator. So the first term here that you would get is, of course, the one you're used to. It gives you absorption, reflection, etc. It's the second term I'm interested in, because now I have sort of AC noise, if you will, the fluctuations of that operator multiplied by my AC signal. And so I will generate sidebands, right? If you want sort of like FM modulation or AM modulation. Okay, and it's so sidebands, which is really what I'm going to measure when I do Raman scatter, right? And so Raman is really, at the end of the day, a probe of noise in the system. Okay, and because noise can couple to almost everything, this is part of why Raman is so powerful, right? So just to orient you, so the most obvious operator that the polarizability will couple to is the lattice displacement, and therefore the fluctuations you would expect to see are phonons. Now, because this is a scattering technique and it's this higher order in a perturbation, it's actually quite weak and also very surface sensitive. And so in my own lab, this is our Raman setup we've built to measure both with great sensitivity and also all the polarization capabilities. But we also can use a vacuum suitcase to bring materials directly into our low T setup with no exposure to air. And so that allows us to really measure them very cleanly in a way that I think no others can in the world. Okay, so anyway, what else can our Raman do for us? Well, if we have strong spin orbit coupling, it's not surprising that we can imagine the polarizability coupling to some operator of S.S. It turns out there are other mechanisms by which that can occur. And when it does, that allows us to see either magnons or spin-ons, basically, or even just thermal fluctuations of the magnetism. Now, because we're looking at a derivative here, it's also quite natural that we would actually get a symmetry, a higher order tensor than we normally see in our absorption or reflection measurement. If you want, you can think about it because there's essentially two photons, one photon in, one photon out. And so as a result, it means that by looking at the polarization dependence, especially as I look at different crystal axes, I can actually determine directly the symmetry dependence of whatever excitation I've seen. Okay, now I mentioned that we can couple to magnons and spin-ons, and we can also couple to thermal fluctuations. In fact, my group had used this to demonstrate that Raman could detect the order in chromium germanium telluride in 2016, and unfortunately not in a single layer. That was our mistake, but anyway. So what you're seeing here are two phonons, one of which actually splits due to magnon-phonon coupling. But the large green background is actually just thermal noise from the magnetism. And you can see that right at TC, that thermal noise is completely suppressed. So this idea was actually then exploited by Hyung-Sik Cho's group very nicely in nickel PS3, where they showed that they could use this thermal fluctuations to detect the order all the way down to 2 layers. And this is an XY antiferromagnet. But interestingly, when they went to the single layer, it seemed like the order was almost completely suppressed. And I actually think there's a beautiful result that needs some follow-up work. But in any event, it shows sort of the power of the idea. So one can also couple to charge fluctuations, again, perhaps not surprisingly. And this is how Raman can really measure various kinds of charge excitation. So for example, in a charge density wave, you can measure the charge density wave gap, or you can measure the amplitude, or if you want Higgs modes using Raman. But it turns out this is also a nice demonstration of where symmetry can be quite powerful, because, for example, I'm showing you here measurements of the superconducting gap made in the cuprates. There's like lots of examples I could have taken, lots of superconductors, which has been seen. But the point is that they use the different selection rules to pick out certain parts of the Fermi surface. And so you could actually measure changes in the gap in different regions of the Fermi surface by just changing the polarization of your light. And you could also, in fact, I'm not talking about that here, but you can also use it to look at different scattering. So if you believe, some region of your Fermi surface is, hot, in principle, you might be able to look at that with Raman scattering as well. So You might have asked, wait, I mentioned something about quantum in this talk. So is there any evidence of quantumness in all of this? So I would say yes. So one of the interesting things that, of course, can happen in quantum materials is you can, in non-trivial phases, generate sort of fractional particles, right? So the most classical example are spin-ons in frustrated magnets. So one of the things my group has done was look carefully at lithium chloride in above its ordering temperature, where it should be close to the spin liquid phase. And I'm showing you the magnetic continuum we see as at different temperatures as a function of energy. And what we found is that the temperature and energy dependence perfectly follows a Fermi function. So we really were able to directly show that it has Fermi statistics governing the excitations in this material, showing that it's really a fractional excitation. There's actually lots of work back in the sort of early 80s where people showed that you could actually also use Raman to detect different quantum pathways and even interference between quantum pathways, in that case, in interband transitions that were detected in gallium arsenide. Okay, so I realize this is a very noisy slide, terrible pun intended. So let me just try to summarize. So basically, my students go to the lab, they take a laser pointer, they shine it at a material. The laser can excite phonons or magnons or plasmons, et cetera. And then I tell them to sit there until we see the signal we're looking for. So that's basically Raman scattering in a nutshell. Okay, so let me dive into the first example I wanted to discuss today in detail. And I'll start by telling you some insights Raman has given us into the coupling of two particles to form a unique fluid. And it's a topic I'm sure we're all kind of well aware of these days. But let me show you the more quantum version. So as I mentioned earlier, we're quite interested in these topological semimetals. And I want to just kind of briefly explain what we find exciting about them for maybe those in the audience who are not as familiar. And this goes back to ideas by Michael Berry and others, asking the following question: if you have some excitation, whether it's charge or otherwise, moving through some phase space, of course, that wave function will pick up a phase. But normally we ignore this phase because it would just go away when we take the probability distribution. However, what Berry asked was, what if that particle goes around in a closed loop? Can it pick up a phase that would not be easily gapped out? And would that have any physical consequences? Right, so imagine your particle lives sort of in some interesting, unique phase space. Okay, then he showed that in fact you can pick up what we now call a Berry phase as you move around in a closed loop. And that Berry phase is just the integral of what's called the Berry connection, which is just the expectation value of the derivative. Right, so put a different way, if I'm thinking about this torus, you know, the Berry connection is like asking how the curvature changes in one given direction. Right? But if I'm interested in geometry, I really want to think about curvature, because now I can see the difference of the torus from, say, the sphere. Right? So the outside of the torus has all positive curvature. It looks just like a sphere. But of course, the inside of the torus has negative curvature, and it actually has points that are not equivalent to any points on the sphere, showing it's topologically distinct. And what Berry showed is that you can actually write the equivalent in quantum mechanics, which we now call the Berry curvature, which is the curl of the Berry connection, and it will behave in a similar way. If you integrate this Berry curvature over a closed surface, you'll get this Berry phase. Okay. Now, this all sounds mathematically interesting, and you can ask, is it really relevant? And indeed it is. It can tell us about things like, you know, are we entering some new phase of matter as the quantum geometry changes non-adiabatically? This is all part of another talk that I'm not going to get into. But another way of thinking about it is this Berry connection looks kind of like a magnetic vector potential, and therefore the Berry, and then the Berry curvature. Is there a question?
No, I think someone just didn't mute themselves.
Okay.
I'll mute them now for you.
Okay, I'll go on. So the Berry curvature therefore looks like a magnetic field. And in fact, remarkably, if you work out sort of the motion of electrons in, say, a band, you'll find that the Berry curvature of magnetic in magnetic space behaves exactly as if the electrons were experiencing a magnetic field. And so you'll get sort of, that's how you get like anomalous velocities or Hall effects coming from Berry curvature. Okay, so with that in mind, are there materials that have interesting band structures related to this Berry curvature? And the answer is yes, otherwise I wouldn't be bringing this up, right? So it goes in some sense back to Dirac. So if you take a Dirac semimetal, so you have this linear dispersion in 3 dimensions, and you either break inversion or time reversal, you'll find that you split your Dirac node in two, right? Into two copies, where the spin is either collinear or anti-parallel to the momentum. So what you've done is to basically create electrons of two flavors, right? Basically left or right-handed electrons, right? Because again, the momentum is either along or anti-parallel with the spin. Okay, so now the next part, what this has to do with Berry curvature, is if you take a cut at finite energy, so that in your left-handed electrons, let's say, you'll see, or yeah, left-handed electrons, you'll see that all the spins point in. It looks as if there's a magnetic monopole sitting at the center there. Whereas for the right-handed electrons, it looks like the anti-monopole. And indeed, if you sort of follow this down to the node, it really does look like you have a magnetic monopole. And whenever you reach a magnetic monopole, your vector potential, or better yet, your field, should be divergent. And sure enough, it turns out that that's essentially what happens to Berry curvature when you reach one of these nodes. So similarly, you might ask, given that you have this chirality, is the transport protected, right? Is it that you can scatter back and forth between these chiralities, which seems odd, or not? And in fact, the transport of these topological semimetals is really non-trivial, no pun intended. So for example, if you look at cadmium arsenide, which is a 3D Dirac semimetal, you find that you have these very large transport mobilities, but again, orders of magnitude smaller single particle mobilities. So somehow single particles scatter constantly, but if you try to move them in the forward direction, they rarely scatter at all. Okay. Similarly, if you look at tantalum arsenide, which is a wild semimetal, you find exactly the same behavior, right? You get large transport mobilities, very short single particle mobilities, at least in comparison, right? Orders of magnitude difference. Okay, so one of the arguments that was made was, look, in a normal metal, you have huge density of states. There's lots of options for scattering. And when you're a Dirac spectrum, be it a 3D Dirac or a wild semimetal, you've dramatically reduced the phase space for scattering. The problem with that argument is tantalum arsenide has 24 nodes in it. So there's plenty of phase space for scattering. Okay, and as I'll show you, there are other examples where this argument would not hold, right? And it certainly doesn't explain why would single particle be so low compared to transport. So you might argue that it has something to do with symmetry, right? So maybe symmetry is somehow preventing you from scattering around. Again, cadmium arsenide has inversion symmetry, tantalum arsenide does not, right? And some of the other examples I'll show you have other kinds of lattice symmetries. Is it somehow protected by topology? I'm not even sure I know what those words mean, right? So how would scattering care about protection from topology at all, right? You know, at most you might have sort of limiting yourself from backscattering, but of course the rest of scattering is fine. So, and to make matters worse, you can just look at other materials, right? So first of all, tantalum arsenide and cadmium arsenide have different topologies, but if you look at, as Dirac told us, tilted cones, you can see that, for example, in WTE2, which is a type 2 wild semimetal, you see the exact same effect. And in WP2, which is also a type 2 wild semimetal, you see again the same effect, right? So it seems like regardless of the topology or quantum geometry of these topological semimetals, you find this kind of large discrepancy between the transport and single particle lifetimes. And things get worse. So for example, if you look at tantalum phosphide, you find there's this nice work out of the University of Florida where they show that you can have materials with huge numbers of stacking faults, and yet you still see quantum oscillations with very large mobilities. If you look at WP2 at very low temperatures has these remarkably long mean free paths of like 100 microns. However, if you look closer, what you find is that the wild node is actually buried. It's actually 300 MeV below the Fermi level. So it's hard to believe that the fact that there's a wild node in the system makes much difference to the transport, especially at low temperatures, right? Nonetheless, the transport in this material is quite anomalous. So you see enormous violations of the Wiedemann-France law. And if you look at the resistivity, you find that actually it varies by orders of magnitude as you heat the sample up, right? In fact, it even looks basically exponential at low temperatures with enormous triple R ratios, right? So that your resistivity is varying from low temperatures to high temperatures by literally 4 orders of magnitude. Okay, so this is really kind of anomalous behavior, and WP2's band structure looks nothing like cadmium arsenide, which does basically the same thing. So our hunch was that the lattice had something to do with all this, and there are various ways to think about that. So first of all, we have these magnetic monopoles. And if we go back to Berry curvature and Berry connection, remember that Berry connection is really d by dk, right? But that's basically the real space operator written in momentum space, right? So just very naively, if your phonons are manipulating the locations of your electrons in real space, you have to ask, what are they doing to Berry connection in the band structure? Perhaps more relevant to our transport discussion, it also seems that phonons are going to be the very natural way that you would go from one chirality to the other, and could be how you would relax, transport or chirality in general. So what you might expect to see is, if you look at phonons, if the phonons scatter only into other phonons, you'd basically see by anharmonic scattering, that the optical modes, for example, would decay into a pair of acoustic modes. And you would just see that the temperature dependence of the lifetime is governed by Bose statistics. In other words, it would just keep growing with temperature, because these are bosons and the chance of making them just gets better and better with temperature. However, there was some infrared work done by Rohit Prasankumar's group at Los Alamos, where they showed that the infrared lifetime, the lifetime of an infrared active phonon mode actually went down as they heated up the temperature. I mean, this is quite anomalous, right? That you heat something up and scattering gets reduced. So they suggested that this could be due to coupling to the electron bath. And so we wanted to follow up on that. So here's our data from tantalum arsenide. We have a similar result in niobium arsenide. So what we found is that some of the modes of particular symmetries, in this case B1, have line widths versus temperature that look exactly like what you would expect for anharmonic scattering. Basically, as you heat it up, you see it grow following a Bose function at omega over 2, consistent with the idea that you're just, as you raise temperature, populating more and more acoustic modes by anharmonic scattering. However, there are other modes that we saw, in this case an A1 mode, and I should mention that this A1 mode happened to be very close in energy to this B1 mode, which is important because naively you would expect their anharmonic scattering to basically be the same. And yet what you see in this mode is quite anomalous. You see basically a rapid rise at low temperature of the line width, and then a slow and steady reduction in the line width. So basically a peak in the line width that actually goes down as you keep heating. Okay? And again, I want to compare that with what we saw from the nearby phonon, which showed anharmonic scattering. Not only do they qualitatively look different, excuse me, quantitatively, we see much more scattering in this anomalous case. Now, the blue line I'm showing you is a fit to the data where we just assume decay into some fermions, right? So basically the difference between two Fermi functions separated by the energy of the phonon mode. So the idea here is that you have your wild semimetal, your phonon comes along and it can excite an electron across the node. And as a result, the temperature dependence would be governed by the difference in the Fermi statistics of these two states. Now, you might be concerned that I'm talking about an A1 mode, which has no chiral components, no angular momentum. So how am I flipping the spin? Well, it turns out, and these are calculations done by Pri Narung's group, that if you account for a reciprocal lattice vector, you get a kind of umklapp scattering, which can easily take you from one wild node into the other via the, okay, and that there's a huge phase space for this kind of scattering. So this is a calculation of sort of the phase space for that kind of process. So that suggested to us that in tantalum arsenide, at least, our data was suggesting that we have very strong phonon-electron scattering, right? So phonons decaying into electron hole pairs. So that was very nice, but the question is it only in this material? So we then went and looked at WP2, which I'll just remind you, type 2 wild semimetal, but with a very deep buried node, okay? And we see exactly the same behavior. Basically, we see phonon modes, which again, their temperature dependence is just entirely governed by this Fermi statistics, right? And the nearby modes, which do not show this behavior, have much, much sharper line widths, okay? So the anharmonic scattering is very weak, and the phonon-electron scattering is very, very strong in comparison.
So can I have I have a quick question here.
Please.
So what happens if the Fermi energy of the wild node of this wild semimetal is so high that Pauli blocks any interband transitions induced by these optical phonons?
Yeah, then you wouldn't see this effect. But the difference here, because this is exactly what I was going to say next, if you look at WP2 very closely, what you see is that actually there are two parallel bands very close together. And so if I zoom into the Fermi surface, what you would see are bands that look like this. Okay, and so there you basically have what we call vertical nesting. So basically you have lots of phase space for a phonon to come by and excite you from one band to another.
I see.
And indeed,
yes.
I was just going to say, indeed, what's going on is I think consistent with your intuition, which is depending on the Fermi level relative to this transition, that governs entirely the temperature dependency you see here, right? So essentially what's happening is when you start heating up, you start creating, you can think of it like basically you're opening up more phase space for scattering, right? So for example, imagine this transition was happening above the Fermi level, right? So you start thermally populating up here, but then at some point you keep thermally populating and now you've essentially have Fermi functions covering both of the two states. And you just reduce, you basically hit a wall. You can't sort of scatter anymore because polyblocking essentially limits you.
I see.
Right, so that's basically why you see this plateau in the temperature dependence. Okay, so that was very exciting. But you might just say, I have no idea what I'm doing, and maybe I can't measure line widths very well, or et cetera, which is maybe fair because I don't go to the lab very often anymore. But anyway, it turns out it wasn't just our group. So there was another group that measured crystals also from Claudia Felser. They actually measured both the inversion symmetric and inversion broken versions of WP2, and they see exactly the same line width behavior. They have a slightly different interpretation, which I think is wrong, but anyway, they definitely, their data looks exactly like ours. Okay, this has also been seen by yet another group in MOTE2 and as well in cadmium arsenide. So this seems to be sort of ubiquitous in all these different topological semimetals that all have these large triple R ratios that you have this strong phonon-electron scattering. So question is, what's going on here? Okay, so this goes back to an idea from Pyrrol's all the way back in 1930. So the idea was the following. So normally when we think of applying an electric field and exciting our electrons, giving them energy and momentum, at some point they scatter off acoustic modes, they lose some of their energy and momentum, right? And the acoustic modes, they move on, and eventually by anharmonic scattering, they scatter into two more modes of lower energy, basically dumping that energy and momentum into the lattice, right? So the point is you add energy and momentum into the electron bath. By electron phonon scattering, they dump it away from the Fermi surface into the phonons. And then the phonons, by phonon-phonon scattering, dump it into heat. And this is essentially what happens for resistance, right? But what Pyrrol's pointed out is you can imagine a scenario where the phonon-electron scattering is strong, such that that original acoustic mode actually decays into another electron. So it doesn't even have to be the same electron, right? Because for your bath, who cares, right? The point is that you return the energy and momentum back to the Fermi surface. And so the result is that instead of dumping so much energy and momentum to heat, you dump it back into the electrons. And so for transport, this would strongly enhance your transport, right? Because basically this electron phonon fluid would kind of be, roughly speaking, dragging each other along such that you would have apparently very high transport lifetimes, but very low single particle ones. Now, it'd be fair to say that everything I've told you about experimentally is for the optical modes, but we worked closely with Prina Rung's group, who was able to calculate the phonon spectra for WP2 and tantalum arsenide. It matches beautifully our own data. But what she showed is that actually the phonon electron scattering in the acoustic modes is extremely strong, such that you have roughly 10 times the phonon-phonon scattering for the acoustic modes at low temperatures in WP2. And we believe that this is really the explanation of this very large difference that you see between the transport lifetime and the single particle lifetime in these topological semimetals. So if you want to know more details or learn more about why semimetals, I point you to our recent PRX, which sort of describes all of this in great and gory detail. But I'm also happy to take questions.
Hello. I'd like to ask, is the acoustic phonon stronger than the optical phonon? Normally, the existing model predicts that at higher temperature, the line width will increase very fast. If you increase your temperature further than 300 Kelvin, might you expect the line width to increase significantly?
Sorry, so you're asking, does the acoustic mode scatter, do they scatter more than the optical modes? Was that the question?
Yeah, this is the first part. And the second part
Yes.
is if you increase higher than 300K, do you see increased line width?
Okay, I think I understand. So but the first part is yes. So the phonon-electron coupling for the acoustic modes does actually seem from the calculations to be stronger than the optical modes. Unfortunately, experimentally measuring line widths of acoustic modes is super challenging. So I don't know anyone who's done it. For the second question, what we find is that yes, there's I don't have the data with me, but if you heat above 300 Kelvin, basically you'd have to go very hot before you would see the enharmonic scattering turn back on, because it's just the enharmonic scattering is so weak compared to the phonon-electron scattering.
Okay, there's a multi-phonon effect. Okay.
Yeah, that's right. So
Okay.
basically what we think is happening is you have both the enharmonic scattering and phonon-electron scattering together, but the phonon-electron scattering is so far dominant that that's what we see at these temperatures.
Okay, thanks.
Yeah. Okay, so in the interest,
yeah, so I have one quick question. Are you able to
oh, sure, go ahead.
to directly measure this electron phonon scattering rate, and how does that compare with the quantum scattering time that are expected for these materials?
That's a good question. So the challenge is I'm measuring modes at roughly Q equals 0, not exactly Q equals 0. And of course, the transport times are averaged over all Q, right? So I mean, of course, weighted and so on, right? So it's not obvious to me that one could compare them directly, if that makes sense to you.
Yeah. Well, the thing is, if so I guess
sorry, let me say one other thing. Sorry, which is to be a little bit more fair to my theory colleague. So Pri has actually calculated the transport lifetimes using her first principles theory, which agrees well with our data. And they match beautifully the temperature dependence of the lifetime in WP2.
Great.
So that's in a separate paper that she has on hydro in WP2. But
great. Yeah. No, so the question I had actually was about the quantum scattering time, not the transport time. The quantum scattering time that is measured in SDH, for example, right?
You mean the single particle time?
Yes, that's right. So, for example, in the
that's
slide,
a good question. So, yeah, I guess I don't have a good answer. It's a good question, but I don't have a good answer for you.
Okay. Well, yeah. So the point would be that if you're scattering very quickly with electrons and phonons, right, then that probably will show up directly in the quantum scattering time. Of course, it's going to be more complicated than its transport time. So there's some kind of averaging going on and stuff.
Correct. So we think that's actually, to make a long story short, we do think that is the explanation, right? That again, the electrons can scatter into phonons as much as they want, right, or they will. But because the phonons give everything back, not everything, but most of it back, that's why the transport lifetime is so far, is so much larger than the single particle one, right? Because again, you have a process whereby single particle scattering could be large, but for transport, it would look as if it was a very long lifetime.
Yep.
That makes sense?
Yeah, it does, yes. Okay, thanks very much.
Yep. Okay, so now I'm going to show you how our post-pandemic tool allowed us to identify and optimize clean and local control of materials just by putting them together. And as I think many of you know, indeed, a well-designed experiment really requires careful consideration of what's been touched. So I hope to convince you that we now know how to do that in 2D materials very well. So speaking of 2D materials, this is kind of an amazing field with this huge array of 2D toolkit, from everything from semiconductors to superconductors, et cetera. But for those of us in the US, at least, and I think probably for you too, as academics, we're always very interested in donors and perhaps being the acceptor. And I want to argue for you that that's the piece that's missing now in the 2D toolkit that we are about to add. Okay, so why would you be interested in that? So you would like to be able to control locally the charge in these 2D materials for a variety of reasons. Of course, the obvious is electronics. You want to make sort of nanoscale diodes, and transistors. You can also, of course, be interested in plasmonics, where being able to control the charge very locally could be very useful for all sorts of plasmonic applications. From a fundamental standpoint, of course, doping is a nice knob for tuning yourself through various quantum phases of matter. And even from magnetic standpoints, it's also quite useful. If you could locally, as you would in a p-n junction, break the inversion symmetry by inducing local charges, you could turn on DM interactions where you could potentially even induce, say, skyrmions, right? So this is if you could really locally and nicely control and cleanly control the charge in 2D materials, this would be a really fantastic opportunity for a variety of applications. Of course, the key is you have to keep it both sharp and clean. So that brings us to the idea of modulation doping. So as you might know, typically what's done in a semiconductor device is you implant either an acceptor or a donor. You might do it very locally so that when you make your transistor, you can, say, be heavily doped under the contacts to reduce contact resistance, but still keep your nice gate in the middle. The problem is when you do these kind of things, of course, your dopants are scattering centers. And so Horst Stormer invented a technique a little over 40 years ago, where he said, let's take a conventional 2D quantum well where you have sort of gas-algas heterostructure, right? And you put a donor in the barrier, and the result is because the donor has higher energy, the electrons will basically fall into the well, right? And so you could then induce a nice charge density in your quantum well without with some physical separation from the scattering center. Similarly, you can do that with acceptors, where there the impurity level is lower than the well, and as a result, you soak electrons out and you can hold dope as well. Okay, so this is basically how fractional quantum Hall effect was eventually seen by making high enough mobility 2Ds. So our idea is that you can do the same thing in 2D materials. So take graphene, right, and imagine you have a material with a different work function. That's kind of the equivalent of your acceptor or your donor, and you should either add or subtract charge. So one example is HBN, which shows that this is actually a little more complicated because HBN actually has a lower work function than graphene, but doesn't donate anything because it has an enormous band gap. So there's essentially no electrons there at an energy where they could be donated into graphene. You might ask about, say, tungsten selenide. Well, it has basically the same work function. So even though it has a smaller band gap, no love there. So what you'd like is a material with a small enough band gap, a deep work function, and perhaps a very narrow conduction band that is just sitting there waiting to soak charge away, right? And then you could think of it as what we would call a crystalline acceptor. So the first case that I'm going to try to show you is ruthenium chloride, a material near and dear to my heart, where you have ruthenium on the honeycomb lattice. And here the chlorine is fairly electronegative, and the ruthenium is not so bad either. So you might imagine that you would have a very deep work function that you could exploit towards it being an acceptor. It turns out it also has an interesting electronic state. So basically the chlorine splits the D level into a T2G and EG level. The T2G further splits by spin-orbit coupling into J1/2 and J3/2 states. Now you have 5 electrons, so you fully fill the J3/2 state, but you half fill the J1/2. And because you've reduced the degeneracy so strongly, it turns out even with moderate on-site Coulomb repulsion, you get a mod insulator. And this is what's called a relativistic mod insulator because the mod insulating state comes about through the combination of spin orbit and on-site Hubbard. Okay, so just to put this all together, we actually did quite a bit of work years ago showing that this is indeed the right interpretation of the band structure. It has a kind of interesting optical response I have no time to get into. But the key point is you have a 1 eV band gap that's very clean. You see no absorption below the gap. And even in the visible, if you're thinking about optoelectronic applications, you find that indeed the absorption is fairly weak. So if you're thinking of using this very nice insulator for an acceptor, you could even still apply it to a variety of optical experiments. Now, if you look at its work function is 6.1 eV. It's quite dramatically lower than monolayer graphene. And so you would expect that there should be enormous amounts of charge transfer from the graphene into the ruthenium chloride. What's more, the HBN valence band lines up with the ruthenium chloride conduction band. And so you might imagine a kind of resonant tunneling where you could actually still have charge transfer through the BN barrier. And this should also work for bilayer graphene. It has basically the same work function. In fact, it might even work better because you have a higher density of states in the bilayer, so you can soak more charges out. Now, it won't work in chrome chloride. So this is another example where it's not enough to just have a nice electronegative system, right? Because here you have a big band gap, and so and a sort of conventional insulator, and so basically there's no states that are useful for either donating or accepting electrons, say, into graphene. However, it does work for tungsten selenide, and I won't show you any of our data, but it's in the paper where we demonstrated that indeed you can use ruthenium chloride as an acceptor for tungsten selenide. Okay, so to be fair, we were not the first to think of this. So Eric Henriksen's group took ruthenium chloride and plopped it down on graphene, measured the transport, and saw very large conductances on the order of 200 E squared over H. And yet when he gated, he would still see this Dirac minimum, okay? But he would get, this was quite confusing because he would get carrier densities from the Hall that were on the order of 3 × 10⁻13. There were a variety of sort of first principles calculations done by Rosa Valenti and also by Una Kim's group. They all show the same thing, that basically you expect the Fermi level in graphene to go about 600 MeV below the Dirac point, quite large. There was also work by the group in Stuttgart where they showed that indeed, if they used HBN to cap, they could get very nice clean layers, except for the fact that while they would see quantum oscillations with carrier densities similar to Eric's, they would see this weird splitting of the quantum oscillations, suggesting there were multiple carrier densities in their system. And again, there's this sort of anomaly in Eric's data of the Dirac minimum. So this made us worry that maybe part of the problem is the fact that you're measuring all of this with transport and you have to do fabrication and you never quite know what that's doing. So we decided to try this with a sort of contact and fab-free method. And our old hero comes back, namely Raman scattering. So this is a Raman scattering in graphene where you have two key characteristic phonons, the G peak and the 2D peak. And the black line is sort of intrinsic graphene, and the red is after it's been doped by annealing. So in fact, what happens is the G peak and the 2D peak, they have different dependencies on strain and doping, and you can make use of that. If you plot the 2D frequency versus the G peak frequency, you see that they either, if you just strain the system, all follow on a line, or if you just change the Fermi level, you can shift them along a different line, right? So basically, this is from the initial device where the graphene had random strain from sitting on SiO2. This is after they anneal it to get the doping level up, and they see a large shift primarily in the G peak coming from the fact that that's much more sensitive to doping. There was also nice work by Nadia Mason's group where they took graphene and they put it on a variety of nanospheres of different sizes so that it could induce different amounts of strain without changing the doping. And indeed, they find that as they make the dots smaller and smaller, you primarily see shifts in the 2D peak because that's much more sensitive to strain. So this is a long-winded way of saying by measuring both the G and 2D peak, you can measure locally with Raman the doping and strain levels completely separate without any fabrication or transport involved. So this is what we get. So this is now ruthenium chloride, graphene sitting on both ruthenium chloride and SiO2. And what you see is indeed you get a huge shift of the phonon modes consistent with a large change in the Fermi level, specifically, again, 600 MeV, about 3 × 10⁻13, consistent with what was seen in the transport. We tried also with chrome chloride, and indeed, as you would expect, you see no charge transfer. You just see basically induced strain from the difference in the lattice constants. So far, so good. Everything looks like it's doing what it's supposed to. So are we really doing modulation doping? Is this some very local charge transfer? So the first thought we had is, well, let's take ruthenium chloride, where we have single and bilayer ruthenium chloride, and drape monolayer graphene on it and see if there's any difference in the doping in the two. So here I'm showing you a map of the G peak of that very structure, okay? So the first thing that you see that's striking is you can, by eye, see the border of the ruthenium chloride, right? So the change in doping is so dramatically fast that it's basically well below our resolution of 300 nanometers. The second thing is you can't, by eye, see where the single layer or bilayer of the ruthenium chloride is. And that's not just your eye, it's actually we've checked, okay? And let me just draw it for you, right? So basically, the point is that even a single layer of ruthenium chloride is enough to give you most of the charge transfer you're going to get into graphene. Right? So to test this idea further about vertical transfer, we tried a monolayer and bilayer graphene sitting on very thick ruthenium chloride. And so here again, we saw that our monolayer graphene was getting doped at this very high level of 600 MeV Fermi level shift. Okay, But interestingly, we find the bilayer, even though it has less shift, because of the higher density of states, it's actually getting more carriers, so about 610 to the 13. Although in fairness, we're still working on this because it's not clear how much of it goes to the bottom of the bilayer and how much goes to the top. And last but not least, we wanted to check with the BN, what happens there. So we took monolayer graphene on the bottom, we put a BN somewhere in the middle, we drape lithium chloride on top. And yet again, we see that the monolayer graphene gives us this nice, very heavy doping. But with a BN spacer, we still see doping into the graphene, even though this BN spacer was actually a 5 unit cells thick. So of course, we see much lower doping on the order of about 50%, of about 0.6, 10 to the 13. But we found that as you reduce the thickness of the BN, you can actually make this doping go up and up and up, as you'd expect for a kind of tunneling process. So what's also nice about this is we can use the Raman to detect the homogeneity. So what we saw was that there are regions that are very heavily doped. And then there are regions where you see both the heavily doped peak and then another peak that looks like it's at the undoped region. And then if you keep going, you would actually see regions that were sort of roughly 50-50. Okay, so the point is what's happening is within our laser spot, some of the graphene doesn't touch lithium chloride. It basically forms a little bubble, a well-known problem when you transfer 2D materials. And because the bubble doesn't physically touch lithium chloride, you basically get no doping in the center of the bubble, right? So we can actually use this as a way of measuring the homogeneity. And if I go back to that first map, what you see is, of course, the monolayer graphene, the monolayer lithium chloride with monolayer graphene is very inhomogeneous because it's a very rough topography. But even just the bilayer lithium chloride gets much more homogeneous. Okay. And as you'd expect, of course, the BN spacer gives you a beautiful homogeneity, right? Because it's just everything is very flat and pressed down. And so this suggests you can make devices that are very clean and homogeneous. And indeed, we've managed to do that working with Eric Henriksen's group. So now we get rid of this direct minimum and we see much higher conductances. And really saying that that original direct minimum was just coming from regions that were undoped, right? Because transport's going to average over everything, right? So this was basically just a measure of, in some sense, the disorder in the sense that there was some undoped region in the device. What's more, from the sort of, say, most homogeneous region that we saw, which was roughly on the order of 95%, we can estimate a size of these bubbles, which is on the order of 65 nanometers. And so that suggests that the vertical charge transfer, which is on the order of a nanometer, and the lateral charge transfer must also be very short. So in this case, it must be less than 65 nanometers. And we were very pleased to see that Dmitry Basov's group, using near-field techniques, detected the exact same thing. So they measured plasmon responses due to this very heavy doping. They get the same doping level that we do. And they also see that in topographic regions where you have these little bubbles, that the doping completely goes away. And you can see this kind of circular sort of scattering of the plasmon off of those bubbles. So this, we think, really shows that this lithium chloride is an extremely powerful technique for this kind of modulation doping, where we can very locally and heavily control the charge in our graphene or other 2D systems. Maybe I'll just take a quick pause here to see if there are any questions before I get close to wrapping up. Okay, so just to kind of tell you a little bit about some future directions that we are moving in. Maybe I will skip this first one and just go to the second one. So this is where we're trying to turn things around and now use our quantum materials as the tool rather than trying to measure them. So we're all very aware that, of course, respiratory infections, one wants to rapidly test for their presence and especially have something flexible that can be easily reconfigured as new infections come along. But it would also be nice to know what it is you're infected with. In other words, not just have a test of a single infection, but rather know what kind of virus is it, or even bacteria, right? Because then you know exactly what the prescription should be, right? In some cases, stay home. In some cases, take thermoflu. In other cases, you have COVID and you better go to the hospital, et cetera. Right? Now, there are very expensive machines that will do this, and they're sort of multiplex PCR, but they require a lot of chemicals. They're expensive, and of course, they require expertise. There's, of course, the rapid version, which you can use at home. The problem with this is it's based on lateral flow immunoassays, and essentially multiplexing is nearly impossible in those systems, not to mention that they're not so great at sort of limit of detection that you would like. So into this, we have brought our ability to do fabrication in the centered atmosphere and graphene, because it turns out, as everyone knows, of course, if you gate graphene, you have this nice Dirac point showing you what the charge level is on the graphene. It turns out, though, there are certain molecules that can easily stack on the graphene just by pi-pi stacking, and they have these little tails that you can easily attach various kinds of probes to, be they aptamers or DNA or antibodies, etc. Now, these aptamers, which are the ones we use, are charged, and so when you attach them, you can actually see a shift in the Dirac point due to the fact that you have this charged molecule sitting there on top of the graphene. But the exciting point is that these probes can be tailored to match a certain biomarker or virus or protein, such that when that charged object comes along, you see yet a further shift in the Dirac point. And the data I'm showing you here are from devices where we were measuring this particular biomarker in saliva. So we can actually measure the presence of this biomarker at clinically relevant levels in saliva. We've now used it to also measure the presence of opioids in wastewater. And we're working on using it to do multiplex detection in saliva of viruses. So just to show you, this is what our devices look like. So we can actually put different, we can put the saliva with different probes in each of the well. There's roughly 5 GFETs in each well. And we can then use them as a way to detect rapidly the presence of various kinds of viruses. At least that's what we're working on. And hopefully it will turn out. Okay, so let me just wrap up. Let me thank the people involved in all this. I want to especially thank Kiping Wong, a fantastic grad student who's with me and did the work on lithium chloride, and Gavin Osterhout, who recently graduated and now is now at Thor Labs. Narendra Kumar, who did all the biosensing and also helped develop the glove box. I want to thank, of course, the funding sources, samples from Nini and Claudia Felser of the various topological semimetals, samples from JQ Yan and David Mandris of lithium chloride. Some of the devices and heterostructures we looked at were actually from Eric's group. We also had chrome chloride from Hugh Churchill's group and HBN from the usual sources. I didn't actually talk about GDT3, so I will skip that. Let me just especially thank Una Kim and her group for the help with lithium chloride, and Preena Rang and her group for the help with the WOW semimetals. And then help from my colleague in biology, Tim Venopainen, on the biosensing, and CBD graphene from Shiling at BU. So just to, sorry, I don't know why I said that. Just to summarize, I hope I convinced you that Raman scattering is an incredibly powerful tool for measuring both symmetry and energy of various excitations, from magnetic ones to electronic ones, that we've been able to use it to see strong phonon-electron scattering, which we believe explains a lot of the unique transport properties of topological semimetals. And we've also been able to use it to demonstrate the first modulation doping in 2D materials with very short and enormous length scales with enormous doping. So with that, let me thank you so much for your time. And I'll gladly take any questions.
Great. Thanks very much for the very, very interesting talk. Questions, especially from students? Well, let me just start. A very simple question. So on this ruthenium chloride, so the purpose was to be able to highly dope graphene to very high Fermi energies, and also in part also to induce this kind of modulation doping. So were you able to confirm that because as we know, modulation doping allows you to separate the charge centers away from the scattering centers away from the plane in which you are doing your conduction. So were you able to confirm the main source of scattering in your graphene devices? So you had these very high conductivities, remember? So
yeah,
you're able to get rid of that. And so So was it coming from these bubbles that, for example, Basov was able to see, or was it coming from very, very far separated charge centers in the ruthenium chloride?
Yeah, that's a good question. So I would say, in fairness, we haven't looked carefully enough at the transport to answer your question. I think Eric is doing that, I would say, as we speak. Basically, I would say the mobilities we're getting are sort of, well, the mobilities we get are as good as anyone ever got at these levels, and frankly better, right? So they're not enormous, they're like 5,000, because at this heavy doping level, you have a lot of electron-electron scattering, at least at low temperature. And then of course it gets worse with electron phonon. So I don't think we're seeing anything remarkably different than what's been seen in transporting graphene in that sense. But also I would argue that we haven't done a lot to get to push the boundaries of mobility. So in other words, you might imagine making, double HBN encapsulated graphene with a very thin, single layer BN on the bottom that's then with ruthenium chloride and et cetera, right? So that hasn't really been our goal. For now, it's mostly just trying to figure out how it works and how to push the boundaries. To be honest, the boundaries we're interested in are slightly different. So one is, can we get to even higher dopings than what I've shown you? Another is, can we find N-type? So can we find donor materials? We're working on that right now. And a third is to really figure out how short are the length scales. And can we then make that use of that to sort of induce interesting charge patterns? So.
Okay, thanks very much. More questions? So I have a whole list of questions, but I'd like to give opportunity to other people to ask questions.
Let me just say, if anyone has questions and they prefer to talk one-on-one, please feel free to send me an email. I'm always happy to set up a time to discuss. But
great. Let's ask the burning question that I have, right? So the burning question I have is about this thing with your electron phonon coupled liquid. Have you considered the role of disorder in such a system? So in a lot of these three-dimensional systems, the way you dope it is by including charge impurities, and these are just everywhere. And so presumably, if you have some kind of finite doping in the system, you already have lots of charge impurities, and presumably they will compete against any kind of relaxation mechanism that you propose, right? So have you thought about how that interplays with your phonon drag type of scenario?
That's an excellent question. So I think the answer is actually okay. There's a subtle answer that has two parts to it. So one is that I think part of what's going on here, which I did not talk about, is you have your Fermi wave vector must be quite long, right? Because you have very small Fermi surfaces for the most part. I mean, even WP2, relatively speaking to a metal, is a very small Fermi surface, right? Mm-hmm. So that long Fermi wavelength means that I think that you would have to have a lot of impurities before they really start to matter. In other words, that the actual impurity scattering is much smaller than you would naively imagine. But that's, I think, only one part of it. So then the second part is, now you add in this very strong electron phonon / phonon electron scattering, right? And that sort of has a chance to win. But that's a mechanism where scattering, if anything, helps for transport rather than hinders. Anyway, I don't know if that if that answers your question, but
sure.
Or just avoids it perfectly. I'm not sure, imperfectly. But,
Sure. Okay. We should have a further discussion on this. It's a very interesting part. Okay. More questions. students, faculty even? I see one or two faculty here. I guess they're keeping quiet. That's okay. So last call for questions.
Maybe just I have a quick question. I missed part of it, so I don't know if it's been discussed. Very interesting talk. So for the last part, when you're talking about this, putting the graphene onto some substrate where you can induce a strain in the graphene, right? So in some cases, when you introduce a strain, there's also this pseudo-magnetic field in graphene, additional barrier phase coming from this very interesting linear dispersion of the Dirac cone. Will there be any experimental signals for this particular phenomena in your measurement?
So that's a good question. So actually, as well, okay, so let me say a couple things. So it requires me to go backwards. So so if I go here, right, so this was a case where they just doped it. This was a case where they induced strain by these kind of nanospheres. And certainly I think one would hope that there'd be pseudofields going on there. In our case, remember, we're putting it on just flat, ideally flat ruthenium chloride. And indeed, you can see that basically there's a small amount of strain, right? So we don't sit sort of on exactly on the just pure charge transfer level, but it's on the order of 1 or 2%. And exactly what kind of strain, actually, unfortunately, it's not so easy for us to tell. So it's probably, either compressive or sorry, we can tell that it's tensile, right? But we don't know, is it, for example, uniaxial or biaxial? So it's hard for us to tell exactly what it is. Having said that, ruthenium chloride's lattice constant is dramatically different from graphene's. That's actually part of the problem with the stacking. So it's actually a very, very large lattice constant. And as a result, we think that's part of where the strain comes from, but it might also just be that it just washes out. So, but having said that, I think it would be extremely interesting to combine, say, pseudofields with this heavy doping, right? So you have, both strain breaking, some interesting pseudofield combined with doping that's very local. So you would strongly break inversion while you have this broken in pseudofield.
Right. How is it easy to engineer this kind of strain in this particular experimental setup? I know there are previous experiments when they just put like dirt underneath the graphene to form these bubble-like islands, right? Where they can see these sort of like pseudo Landau levels because of this trigonal strain.
Yeah.
So
it's that's an excellent question. So easy, no, but doable, yes. Let me put it that way.
Okay.
So, but combining that with ruthenium chloride is yet another story, right? So, yeah, that's there what we would have to do is prepare graphene on a properly, basically a substrate with pillars, so that you would kind of drape over the pillar and then bring ruthenium chloride in from the top. So that's actually something we're thinking to do eventually, but we're not there yet. So
I see. Okay, yeah, thank you very much.
Hello. I have one question, just building on the previous question. Should I go ahead?
Sure, please.
You say you place this RuCl3 on top of graphene, and previous question was based on strain. So I was wondering whether you what do you think is the effect of when you essentially the twist angle between RuCl3 and graphene? Have you what do you think will happen? So essentially that's the strain, right? You found different boundaries or grain boundaries sort of stuff.
So the answer is depressing, which is to be honest with you. So initially the theory was telling us, one of our theory collaborators was telling us that actually you could control the charge transfer by controlling the relative rotation angle. So we made actually quite a few devices where we well controlled the rotation angle between the graphene and ruthenium chloride. And at the end of the day, we saw exactly no difference in the charge transfer. So it seems like the relative rotation angle makes no difference. Now, the reason for that, I think, is because ruthenium chloride's lattice constant is just enormous compared with graphene. So there's, if you wanted to say, for example, CMRA, you would never get one. The only way you'd get one is if you consider like the second atom unit cell. And then even then it would be very long wavelength. So I suspect that's why the rotation angle doesn't matter. Unfortunately, we were hoping this would be another, way to kind of finely tune them, but it didn't work, to make a long story short.
Okay, thank you.
Yeah.
Okay, I think we've kept Ken long enough. It's probably really late for you. So let's thank him for his very, very interesting talk and very good answers to the questions. Yeah, thanks very much.
My pleasure, and thank you for the invitation. And hopefully someday we can do it in person. But
of course, yes, of course. Yeah, let's hope that day comes soon. Yes.
Yes, indeed. Anyway, very nice seeing you again, and happy to follow up with anyone via email.
Okay, great. Thanks very much.
Take care.
Take care. Yeah.